Alright, hello, welcome back. Let's see where we are right now. Yeah, we're doing this whole debugger thing, and I do have some plans now to implement perhaps some TUI stuff. We'll see what happens with that, but to do. There we are. So what I want to have is showing, like being able to show like memory view, instructions view, like IR instructions view, like different views. And I'm thinking like source code view, and yeah. So what I'm thinking here is like, yeah, we have all these views. Now I come from a web design background, so I was thinking like, and I've been using you know, ImGUI as well, so that's kind of like not two sides of the same coin, but it's two different ways to build a UI. And what I'm thinking is maybe we can build like a TUI library that like a very simple TUI library that will just manage some areas of the window, some areas of the terminal, and where you could like, yeah, print some stuff, and yeah, we can see what happens there. So very basic, but let's see what we can do with that. So because right now it's like I'm wrestling with this, just this prompt a little bit, and building a little bit more specific to the prompt right now, which is not really the ideal way to do things, because that's not what I want to have in the future. So I'm thinking we could build a TUI library, which could also potentially be something that could be exposed to in some kind of built-in library in Runic as well, because it's all terminal based, you know, so that could be like extended, or well, we'll see what happens, but that is the idea. So maybe, so I will add this like TUI lib question mark here that we can maybe start on today. So and then for the debugger, let's see, yeah, we probably need more things, but now it's nice that we actually have this, so we can potentially, I mean, right now we can actually go ahead and look at, for example, this script, and then press a button to step through here. And oh yeah, that's right. So I actually yeah, I need to remove some, whoops, some debug logging here. And then we probably need to implement some more of these things, but we have enough now to make it feel okay to work with. So let's see, did we have like self.log, or what did we have actually? Yeah, this part we can remove, or I mean, we don't do this. Was that enough? Okay, I want to remove the after slice as well. Or is it after? Like this. Where did I put this here. Right. Okay. Okay. So so apparently if we get unknown command, we don't clear the thing. So let's fix that. Where are we clearing? Consume all. Run command. Parse command. So it says unknown command returns null. I see. So I'm gonna put this over here then. So whatever is gonna happen, we are consuming the command. Yeah. Okay. There we go. Yeah, and now I can press up and step through the whole program here. Oh yeah, another thing that I want to have is the output as well. Output view, standard out, standard error, combined, something like that. I'm not sure if I'm gonna get to this now though, the 2lib stuff. I guess the debugger is like good enough right now. I just want to get to implementing more IR stuff, to be honest, so we can continue with the implementation. Actually, that should have more priority. Yeah, compiler. Yeah, I mean the compiler has a bunch of stuff, so we do have address mapping, and we have this. What else do we have? We have a lot of stuff. We have if else. We have read-only data. You know, instructions. Building up the context. We have labels. What else do we have? Refs. Struct types. Structs. Now those are, well, we don't have like creating your own like user defined. We don't have user defined struct types. We do not have struct, like you can't create you can't define a value to a struct right now. It's like an internal thing. So this would be like userland structs, I guess. It's like more of an internal thing right now. But yeah, and then we do have scopes, but I'm still not really exactly sure how we're gonna deal with that right now. And we got like these things that we need to get in. So basically what I want to work with right now is the pipes. I think the pipes are gonna be the main thing we need to figure out for this compiler to make this work it's like the pipes and then also blocks and blocks as pipes. Like these three, if we get these three, then everything else feels like it kind of falls into place. Like these three are like the backbone, and then everything could be kind of built, well, not really built from this, but it could, this would be like the proof of concept here. You could say, like, if we get this in place, everything else should be easier to implement, or well, or rather, this is like the hardest thing to implement. So if we implement this, the rest should be just working through it, basically. Yo, Penguin, what's up? Because I need to kind of figure out how it should work, really. So that is what's gonna happen. Okay, so we need to figure out the pipes. Pipes is like step number one. Blocks, so pipes should lay the foundation here, and then blocks are also like this, kind of like two things here. The pipes are like, well, the blocks are kind of like, we're laying the foundation for functions to work, basically. Blocks of code to be able to execute in a context. And then the pipes are the glue between the blocks of code. So these are two sides of the same coin, you could say. The pipelines, it consists of both of these things. And the thing is that pipes, sure, they work with pipelines. If you only have like executables, then that's one thing. But we want to generalize it with like functions, function calls, blocks. So yeah, so when we get like, I think we start at pipes and try to make that work, and then we want to generalize whatever can be piped. And also it's gonna be, you know, the data that's gonna flow between the pipes are also not just gonna be streams of bytes, but it's gonna be typed pipes as well. But I think the first issue that we need to work out is, what are pipes? Where are they stored? And I think to be able to support pipes, we need threads as well. We need virtual threads. I should say virtual here. That are working in parallel. And I'm not sure about the scheduling part of it yet, but yeah, it's probably not going to be the huge issue, because the threads that take care of pipes, they are probably just going to churn through one streaming. Like, they're just going to check, okay, is there data available in the pipe? Okay, stream through some of that data. Is there and then we go on to the next thread. So it's basically, they're going to be super quick. So I don't think we really need a scheduling structure here. We just basically have a queue, and we're going to churn through all the threads, and then the main thread is going to have its is going to do some work. I mean, what we could do is we could differentiate the main thread, because that's going to be the main execution thread. That's where all the execution is going to happen. I mean, that's going to be like where all the non-pipe stuff is going to happen. the threads, the virtual threads that's going to be spawned are basically, they are only going to excuse me, stream data from one source to a destination. That's all they're going to do. So they are very basic, very simple, and they just do one thing and then they're done for their turn. So basically how it's going to be is like you have the main thread. So that's 0, main thread, let's say. And then you have like a bunch of pipe threads. So each pipe thread has, you know, it has a source and a destination, and it's just gonna churn. It's just gonna check, okay, is there, it's just gonna check like if bytes are, or it, maybe not bytes, but if data is available on source, then stream, or yeah, consume that data and forward it to destination. And that's basically it. Then the destination will actually it will receive the data, and depending on the type of destination, like it could be an executable standard out, it could be a functions standard in, which is like it's a pipe in itself, which could be then connected to something else, and so on. So and then otherwise so these threads they will have a way to kind of exit out their, well, this is going to be their turn, so this is the whole turn return. So when they return here, we're going to move on to the next thread. So we're basically just going to loop through all of the pipe threads, do this once for each thread, and then move on to the main thread, which is gonna, so here we could make a choice. So here we could say that, okay, well, could we execute maybe, I don't know, you know, a bunch of instructions on the main thread until we then go through the pipe threads, or do we just do one instruction and then do all the pipe threads? Like, how do we want to do that? So here we could make a choice there to try and say that, okay, well, let's make, I don't know, 10 instructions or something on the main thread and then do everything on the pipe thread. We could even say that the main thread is currently like waiting for another pipe to complete. In that case, we should just, the main thread is like kind of sleeping, and then the pipe threads will churn through until they're done, and then the main thread will continue from there. So we could have a little bit of mechanisms like that. But I think for the first iteration, we're probably just gonna very naively like just have these as different threads. Probably gonna differentiate main thread with pipe thread, or it's just gonna say that, hey, the first thread is always the main thread or something like that, and then we have a bunch of pipe threads, and then during execution we would go through all the threads and just execute their thing. So these threads are not really, they are not really like threads like in the language, like you can create a thread in the language and have instructions being called. They are basically just internal things that happen during main thread execution, or yeah. So that's what's gonna happen there. Let's just have something like this. Execute next instruction. So this is basically where this is one execution step, I guess you could say. So this is one execution step. First we're executing the main thread next instruction, or if it's it could also be waiting for a pipe, I guess, as well. If it's waiting, so we could basically, we have to have a mechanism for that, because otherwise it will, what instruction do we execute? Like, do we have like a, because we're not going to have like a while loop, where I guess potentially we could have a while loop that waits, but it's probably better to just say that mark the thread as wait for some kind of pipe, and that could have a handle on it. We could, I'm not sure exactly how to identify those things right now, but we could have that. So we could have like if, so one, if thread is asleep, wait for wake up. Okay, check wake up condition, yeah, and continue to pipe threads 2, otherwise execute next instructions and continue to pipe threads. Okay. Kind of good to go through this a little bit like pseudocode before, when it's a little bit more, it's something when you have not like done something before and you need to kind of lay out, like I have a basic idea in my head, but it's also like, okay, well, how is it exactly gonna work? It's like very different often from what you've thought from before. So this is a process of like breaking down the problem here and figuring out like how, like what issues could arise and what problems we need to solve along the way. It's good to keep in mind so you don't paint yourself in the corner, basically. Okay, and then we just go through these. This is just gonna be like an internal thing. So this is going to be super easy, I think, this part here. We need some way of like some way of like removing the pipe threads as well. So it's going to be like removing itself or just marking itself as not open or closed or something. I don't know. If we consumed, if stream ended, remove pipe thread. Yeah, we're gonna figure it out. We don't need to write down every single little thing here, but it's good to go through a little bit to see. I didn't really think about this, like, oh, we need maybe probably a way for the main thread to be asleep, because otherwise it's like, okay, well, what's the next instruction? We can't just move forward. If, let's say, we want to wait until the execution of a program is complete, which we do need to do in certain places, then we need to have this mechanism here in some shape or form. So and that's good to think about now before you start doing things. But okay, I think, yeah, so this is gonna be required, I think, for us to support the pipe. So we should probably start here, actually. Now we could also build threads, generic threads for the program to be able to do as well, I guess. It's gonna be able to, we do need to do that as well if we want to support things like background execution of functions, for example, or blocks of code even, or just any expression. So that we could do that. We could also have generic threads that are not pipe threads, that are just executing some kind of code. And then the question is, okay, how do we assign the code for them? Do we just spin up with some context and go? I mean, we could do that. We could just tell it to, hey, this is the instruction address that you need to start at with this context here, and then just go until, I guess, it's done. And it would have some kind of process ID, like virtual ID. Yeah, we could. I'm gonna add this to the documentation, or the kind of sketch here. So we'll have the main thread, and then we'll have I guess this would be more like background execution threads. Background threads. And it's basically going to be the same as the main thread, so it's going to be the same. And now I guess we don't really need to say these things, and then after this check we would, yeah, it's just going to be implied that we're going to go through all of these. So in this case we're going to go through just in a queue based fashion. Everything is going to be in a list. We're going to have the main thread. It's going to be, I guess, interleaved with a bunch of background threads, pipe threads. It could be jumbled up anyway, shape or form. We're going to check what type of thread we have. They could exist potentially in different lists as well, so that we know that, okay, these are all going to be pipe threads. We don't need to check which thread type it is. We don't really need to check the thread type of this. So we can have like a list of these normal, I guess, threads, and then the pipe threads are going to be their own kind of thing. Something like that. Because these two threads are basically going to have the exact same. I'm pretty sure. I mean, there might be some difference, maybe when they're like exited or something. When the main thread exits, we should. No, wait, actually, yeah. When the main thread exits, we need to kind of wait for these as well. Yeah. Of course. So there are differences. So we should probably keep the main thread in a special place. And then the background threads are a list. And then the pipe threads are another list. When exiting, or we could just say that they are the same, but in the main process, like the script runner, it would just check, okay, how many threads, are there any threads still alive? So then just go through those until everything has exited, and then we should be done, right? So exiting the main thread shouldn't do anything special, unless you want to kill the background threads, but that's going to be an explicit action, I think. That's just yeah. Okay, and then so let's add here when all threads have exited, exit the program. And I guess it's gonna choose whatever. Actually, it is a little bit special, the main thread, because the exit code of the whole process is gonna be the exit code of the main thread. So actually, when this exits, store the exit code so we can return it at the end of the program. Okay. With the exit code from main thread. Yeah, that makes sense. And the background threads, they are also going to be bound to some kind of process ID. We should probably have bookkeeping of, let's say you're starting up a function in a background process. I think probably all functions are gonna be ran in background threads. Maybe. No, maybe not. Maybe that's gonna mess up with the what about the closures? Yeah, the closures are tricky, I think. Alright, I'm just gonna BRB 1 second here. right. Okay, yeah, so we're gonna need some of that. Okay, well, I think that's enough of this. Let's just start trying to do this here. Okay, so where do we go? I think we'll start here. I'm actually gonna move things around a little bit. This file is starting to become a little bit too much in here, so I'm gonna organize this a little bit. So we're gonna need so this would be the context there, and for the context we have the read only. What else do we need? Value. Excuse me. Let's put that in its own thing as well. Oops. Value. There we go. Shit, we need like the endian and stuff. Constants. Endian. Alright, type address. Sure. I'm not sure what to do with this type stuff. I want to incorporate the other type information in here as well, but for now this is gonna have to do here. Okay, that was done. Instruction address. That's done. Okay, cool. Ref. Sure. Put that there. And location. Which is this? Context. And the context itself. There we go. Alright, labels. Instruction address. Allocator. the last thing. Okay, cool. Alright, there we go. Now, I think maybe this one would be more like actually no, this is not roots actually. I think we can just remove this. There's like IR zig in here, which has everything. I'm just gonna delete this. What else do we have? Instruction address. Ref. Instruction. Value. Just so we can get to everything from here. Location, yeah. Now some of these I might want to expose directly instead of doing all this. Like doing like, if we only have one, yeah, maybe it's better to just do this. And you only have like, well, you have scope location as well, but whatever. And you have value, except you don't. No, you should. You do. You have only instructions, so let's just do that. You have the ref. Same thing here. Oops. You technically have two things, so whatever. Let's just add those two things here. You also have two things. Whoops. Label and labels. Alright. There we go. If we're missing anything else, we don't care. Alright. You need value, labels. Alright. Cool. Now, why do I still get this? Oh, these things. Right. Yes, that's true. That's true. Well, actually, we could just import this one to get the same thing, basically. Compiler, evaluator. debugger. Runner. Okay. Another one. Okay. Let's just double check if everything works. Seems to work. Yes. All right, cool. Now, okay, so we got a little bit more organized, I guess. It's nice to not have to search, like, I don't know, some people, they like to have everything in one file, I guess. I mean, you can technically search for text along, but I don't know, I just get a little, there's something mentally taxing about knowing that you're in this large file and you can like move up and down and stuff. I don't know. There's something weird about it, but okay. Now, so in the context, so okay, now we need to separate the things here, because the context is actually, this is now for one execution here. This is one execution context, but we are going to need one execution context per thread. So, because I was thinking, hey, we should add threads here, but that's not, well, technically we probably should, well, we should have another context, really is what we should have. This is like for one thread, except it's intermingled between the context of yeah, here. So this is what I gather should be shared between threads, which is the read-only data, since you know it's safe to read from, since yeah, you're not gonna, no one's gonna touch it, so that should be safe to share. Instructions are also read-only, so they should be safe to share as well. The struct types are kind of read-only. I mean, they are read-only, basically. They are not, well, actually they are probably read-only. I mean, technically you could potentially create, like, if we allow dynamic types, or I mean not dynamic types, but types like being created on the fly, like being created during execution, then this could be a mutable list, but that you can only append to, so that you could append to this list, but it would be, the things that you append are going to be constant, so they are going to be read-only. So this should also be, you know, not really a problem to be shared. And then the labels are of course just address, like address aliases, so that's also constant there. And then we have what we can share, or what we can't share is, well, what we're gonna need per thread is the refs, which are kind of mutable locations that you can create at any point in the execution and refer to at any point as well, which we probably need to have some type of garbage collection on, but we don't right now, but anyway. And then we have stack and the stack counter, so that should definitely be per thread, because otherwise you could have things like a function being called, you push a bunch of stuff on the thread, like local variables or something, and then, or even a function call like the arguments. Well, I guess that's what you're doing, but the function arguments gets pushed on the stack. Then all of a sudden you switch to another thread and it's gonna pop some stuff because it's done with its function. So then your stack is all messed up now. So that's not gonna work. So this needs to be per thread here, the stack and the stack counter. So it's basically, yeah, we're gonna set up a stack area for each thread and a stack counter. So that's gonna be good. I think it's like, yeah, we can see here the stack is like 10 megabytes here. So kilobytes, megabytes, 10. So each stack is going to be 10 megabytes per thread. So that's the same that apparently it's the same that Linux has. And then we have the instruction counter, which of course also needs to be per thread. Yeah. So yeah. And then we probably need like the process ID or something like that, like some kind of virtual process ID as well, but that we'll figure out. But I just wanted to go in here and check to see what we need to separate here, basically. So we need a thread context, struct, and we need, so this is going to be the program context, and this is the local thread context here. And the read-only part we already kind of have here, although we could move labels in here actually, and the struct types almost. We could also have it, we could also name it like shared context. Perhaps. Shared context is going to be this, and this. That's the shared context. So we'll put this in there. And then I guess the struct types are just a list. So right now it's not mutable, but I mean it could be mutable in the future. Maybe not actually. Maybe we could statically analyze all the struct types, because Zig does it, but then we need to kind of, I don't know. We'll see what will happen with that. Okay, so anyway, then these are the thread context. So I'm gonna I'll just move everything into thread context. There we go. So that's the thread context. We could also change this to be the private context and the shared context. That's kind of like a lot more descriptive of what's the difference here. This is shared between threads. This is private for one thread only. And then this context, I'm gonna rename you to thread context. And what we're gonna have is we're gonna have the shared, which is gonna be a pointer to a shared context. And then we're gonna have the private, which is the private context. All right, and the read-only, I mean, really, we could move labels in there, actually. Let's just move the labels in here. doesn't really make sense for them to be, because they are read-only. It doesn't really matter. Like the read-only is like, it's really not a... I thought I would organize things a little bit, but I'm just gonna do this now. That's fine. All right. And we can remove read-only actually. Now this becomes a little bit more complex, so I'm gonna do this. Whoops, I mean this. All right. Okay. And let's change this to this here. Okay. All right, so this is going to be the context that we're using for the threads. But now we also need a program context. All right, so this is going to be the entire thing. Which is going to hold all the threads. It's going to hold all the if we need to bookkeep the process IDs, map the exit codes to map the results and everything to whatever. Maybe it's gonna end up here. We'll see. But as like a central point for that, we'll see. Could be good for debugging purposes as well to have it centralized as well, and not like all and about in a bunch of refs in random memory somewhere. But yeah, so we're gonna have like the background threads. I think what we'll do is we will say actually, yeah, let's do this. Let's have threads. So these are all the threads that we need, and basically we just need the thread context. That's all we need, I think, for that. We're gonna have the shared context. So this is where the shared context is gonna live, and then we'll have the thread context. So this basically is just gonna be an array list of these thread contexts. And I'm thinking maybe we should have the pipe threads in its own list as well. Maybe it's not necessary. I guess we'll find out. I think we'd need to have it though, because I mean it kind of depends. It's like it depends if we want to encode whatever's happening in the pipe threads in the language itself, or if we want to just have these special kinds of threads that have a specific purpose for the pipes. Because we actually now need to have like a pipe thread context, which I don't think it actually needs shared information, because it doesn't really do any instructions or anything like that. It doesn't need data, it doesn't need instructions, it doesn't even need a private context. It just needs to what it needs to have some kind of pipe handle that it's supposed it has like a source and destination, but I'm not sure what those will be yet. And these are like pipes or pipe, I don't know, openings, pipe end or something like this, you know. And then pipe end is whatever that's gonna be. Like we already solved this issue, this problem in the other version of the interpreter, but we need to solve it in this way as well now, since we're moving to the IR stuff. So But this is probably gonna be something very, very similar, or if not exactly the same. But we'll see what we'll do with this. But basically, we're gonna have this thing here, and because the pipe tray doesn't need anything else really. What it could be doing is perhaps, well, it depends on the pipe end. But if the source, so the way we have it right now, the whole pipeline, well, actually the pipeline could keep, okay, whatever. I'm not gonna think about that right now. I was thinking about the exit codes and it's gonna forward through some kind of error or something, but now let's just figure it out here. So yeah, so the whole program context is going to be shared. The shared context, we only have one shared context, and then we have a bunch of threads, and then we have a bunch of pipe threads, and I think that's it. We could also potentially, as I've said before, like add the bookkeeping of the processes themselves, like mapping some kind of virtual process ID to a thread, and like storing the results of those threads, of those execution results in there, something like that. But yeah, that's gonna be it for this here. I think maybe I don't know. So that's gonna be that. And yeah, now we need to restructure the whole thing basically. Almost. So we have the runner. We could start here because this is dealing with some of the context stuff and all that. So question is, do we want to add it here? Because how we're doing it is basically we call this compile, which gives us a context. But this is basically what this gives us is really not the context. This is basically gonna be the, I guess it's gonna be like the shared context. We have, yeah, this is all the shared stuff. The rest is basically just create, like it's just initialized. So this would be like context, shared context. Well, okay, the stack start. Oh yeah, that's a constant actually. That should be in the constants, to be fair. Perhaps. Unless we have some kind of per thread setting. How large the stack is. I mean, we could have that, but where is that stored actually? I think it's in the private context. Yeah. And here is context. Share, I think. Yeah. So read only is. You know what? I'm just gonna change this to page size like this, and then we'll import it. No field name read only. Alright, this I flattened it, so there we go. Alright. So the debugger, right? So this should be the program context. No. And this one is actually let's make this the program context, and then we compile to get the shared context, and then we just initialize. Let's just add an init function. Go, and we just add .init shared. Context data size. Now we can add these kind of forwarding functions here. So let's just add data size, and this will just return self share data size. There we go. And this one we could also say like get data or something like that, perhaps. Get read-only data. So we don't have to refer to this inner workings. Read-only data. Struct types. Instructions. All right. Context is the program context. Labels. This would give us labels, which is just labels. And I guess, like when it's, I don't know what I'm trying to say. Like here we're trying to get, okay, this is basically, this is just debug information anyway, so whatever. All right, let's see, we don't have read-only. let's do that as well. Context, it is private. All right. Almost there. Evaluator, this should be a program context. No, program. All right. So instructions, instruction counter. Now we could have a convenience for this. And this is the private. Actually, oh, right. So actually, okay, we're trying to talk about the current instruction in the evaluator, right? But this is going to be per thread. Right, so this is where we need to change this here a little bit. So we have the program context. So what does it mean to step now? Do we just step? I mean, I guess it kind of makes sense if we just step in one thread, like one. So we need to know which thread is the current thread as well. In that case, we have like a thread counter. Yeah, we could do that. Although I'm immediately imagining issues where if a thread closes and the index gets messed up of the counter because of that. I mean, yeah, it could be solved in a number of different ways. But yeah, that's something to keep an eye out for. How should, I mean, we don't, that's one way of solving. I guess we have a thread counter that describes which thread we are on right now. I guess also what we could do is say that, hey, well, if a thread closes itself or wants to close itself, we don't remove it from the list until we're done with all of the threads in the list. And once we get around to the main thread again, like once we've gone through the entire list, then we do the cleanup. So we keep all the threads that have been closed in a list, then remove them between the thing. Yeah. So let's add, in the program context, we will add a thread counter. Starts at 0. Now I think the pipe threads are probably going to be, they're just gonna run through. It depends on how we want to like debug those. Like, I think what's gonna happen is basically we're just gonna run through them. We could add, maybe we could add. We'll see. We'll see what happens with that. But we'll have the thread counter, and then we also need threads to remove, which is also an array list of, I'm gonna say indices. Probably also need like pipe threads to remove as well in that case. But what I'm gonna do is I think I'm gonna wait with the pipe threads maybe, although those are probably the thing we're gonna create first or test first. Okay, whatever. Let's just have pipe threads to remove as well. It's just that it adds so much complexity, but okay. Anyway. Yeah. And then I guess we can add a function here that's like close thread index, but the index is nah. It's probably better to have some kind of ID. Yeah. We're just gonna have an ID, and then we need like a thread ID counter starts at 0. So whenever you create a thread, it's gonna give this ID here, and then it's gonna increase the thread ID counter and so on. Yeah, because then when we remove threads, so this is going to be a U size. Oops. These are thread IDs. You are a thread ID. You don't make sense. So when we close a thread, we actually have the ID here now. So this will be an ID. And actually now these, well, these are array lists. They could be sets as well. Probably better to be sets actually, maybe. Auto array hash map. Thread void. Yeah, I mean you can add as much complexity as you want here. I mean we could store the threads in a hash map instead, and then have lists of different, I don't know, priorities. I don't know. You know, you can like you can have a sorted list of priorities that you would run the thread through or something. I don't know. Anyway. Because I was thinking like, hey, let's change this to an array list or hash map, but no, let's just keep it as a list. It's a lot easier right now anyway. Okay, but these could be sets. So these are sets basically now, because they have void here. So they are sets of thread IDs. So if you add one that already exists, it doesn't do anything. If you can remove by ID, it's fine. You can check, and then when since it's an array hash map, you can also loop through it easily as well. So that's what we need from that. All right. And basically, yeah, when we close the thread, we will just say threads to remove. And then we put the ID. Sure, let's keep an allocator around. Sure, it's probably warranted to have one per program. So now we need an allocator here as well. You can actually get you can actually be an error, so whatever. This can be an allocator error. Okay. Now, it should be pretty easy to spawn a thread as well, because the only thing we need is going to be, well, not an ID. We're gonna need the things we need to like create a thread context. So threads, and then append, and then the thread context. And we can basically just accept a thread context. I'm just gonna see, what do you actually need? You need, well, okay, maybe not, because we need to set the ID. So actually we just need a private context. What? Why are you all okay? Init private context, and then just give you this. Yeah, but I'm gonna also add thread ID here. You're not supposed to call this directly. It's gonna be the program context that gives you this then. So we're gonna get the ID. It's gonna be self new thread ID. Of course. Thread ID counter. And of course you need to be mutable there. You also need to be mutable, I'm pretty sure. Yeah. So we're grabbing a new ID, and then we append dot init with the ID and then the private context, but we don't have the private context yet. So what does the private context need? The private context needs instruction counter, which is 0, everything. It doesn't really need anything, actually. So I'm just gonna add an init function here for convention's sake. And then I'm just gonna say .init here. And since we don't need anything, we don't actually need to pass in anything here. What we could do is maybe we could like return the thread ID so that you can actually talk about this thread somehow. So that's it. Because everything else should be in there. Like, actually, that's not it. Sorry, that's not it. The thing that we need to pass is basically the instruction counter. These things, well, maybe stack as well, because you might want to actually supply arguments to the function. Like, let's say you spawn a thread in which you want to actually call a function. We want to then set the instruction counter to be the location of the function, and then we want to probably push some stuff onto the stack that is going to be the arguments of the function. We don't need any refs, but these two are probably gonna do. Now we could you know, since we have the ID, the thing that actually calls spawn thread could manually set that up as well. We could also have a get thread context. Which gives you a thread context. Okay, now it would be good to have an array list, actually, or a hash map, I mean. Because now we need to loop through the threads every time. but whatever. Let's just do this naively here first. So this would be the threads items. So we're gonna do like 4. And this is the thread context. If the ID is equal to the given ID, we will return that, otherwise we'll continue. Now there should be another else here. Actually, you could also do this. We'll do if they are the same, we'll return TC. If we get down here, we didn't get anything, so that should be like an optional, I guess. All right. Now we probably want to make it a pointer, because you probably want to change things in the thread context. Maybe you only want the private context, actually. I don't know, actually. Or maybe the private context is also a pointer, so that you can change it from, if you have a thread context, you can change it. You can also copy it freely without worrying about the things. I mean, this is copyable anyway, but what the hell? Let's just make it a pointer. There's a you know, there's gonna be cache misses, I guess, but whatever. Probably, because they are right now they're stored in a list. Now all of a sudden this is a pointer, so now they're gonna be stored in like random places. I mean, I get it depends on how you allocate it, I guess, but yeah. Okay. Anyway, so actually now we need to think about like de-initializing the threads as well, but let's worry about that later. So when we spawn the thread, actually now we simply don't have this. We should have a pointer now instead. So we actually need the private context. It's going to be create this. And now this is actually an allocator error here. And then actually it would be allocator error anyway here, so and private equals init, and then we pass this in there. There we go. So now we can safely return this as a non-pointer, and it should still be fine. All right, cool. All right, so let's see, where are we now? You need an allocator, yeah. Hang on, do we have an arena? No. Maybe that's one step up. Okay, so you complain here because you are getting a shared context only. That's right. So this is the shared context, and we need a program context. And I'm going to use the arena allocator. And there we go. Right, let's just copy it in there. Okay. No field name instruction counter. Right. So now I think we're at the point where we need to implement the actual execution here. Now this is the debugger. I'm gonna start maybe in the other end, perhaps here. Right. I mean, maybe we can even move. Like, what do you actually do here? This is the evaluator, right? Yeah. Yeah, so this is like, so this step function is like global for the whole program. So now we actually need to check which thread are we looking at, and we need to step through that thread here. So we need to get the current thread, and actually let's add some more convenience things. Get current thread, which is the thread context, and we will return self get thread context, and then the ID. No, actually this would just be self threads items self thread counter. Super simple. And then what we also want to have is we want to have advanced thread counter. Which is going to increase the thread counter by 1. And then we're going to check if we are at the end. So if thread counter is equal to more than or equal to threads items length. Actually, let's do this. If it's less than length, that means we should be able to do it one more time. So we can just return. Otherwise, we are at the end of the counter. So now we need to process. We need to remove threads, prune threads. I don't know what to call this. Remove threads. I'm just gonna call it remove threads. So this will simply go through threads to remove items or values. No, actually keys, because it's a set. So here we get the ID, and we simply remove that ID. So now we actually need to loop through threads. And we need to say if item ID is equal to ID, we will, yeah, we can do swap remove. It doesn't really matter. The order doesn't really matter. We can swap remove. Yeah, I mean the order matters. I guess the order matters for pipes, perhaps, because if you create the pipes in the same order where the data streams through, it would be the most efficient way to stream the data through, perhaps. Because this is not the pipes though. This is different, actually. So this doesn't matter. So we can do we can change the order. It doesnit's really matter that much. And then this would be I, which we don't have, but we get it from here. So it's a very slow operation, this or very slow, but it's not that slow. It depends on how many threads you have. You're not gonna have like a super large amount of threads probably here anyway. So, but yeah, going through all the keys, and we're looping through those. I mean, this could be sped up if we actually store the threads in a hash map instead, but whatever. So we'll do that, and then we will break the inner loop, and I keep on doing the thing. Now, also what we want to do is we want to defer threads to remove, clear, retaining capacity. We don't need to free the thing. So that will remove all of that. Now we can also do the same thing for the pipes. Pipe threads to remove. Now here potentially the order could matter, so we could do an ordered remove. However, that's way more work. We could do this, but nah. Then we have to sort the things and everything. Now, there we go. And then we also do pipe threads. Now we could later merge these two. So the pipes threads to remove actually, the pipe threads are actually the same as threads. So there's no distinction between them. But I'm gonna have a little bit of distinction right now anyway. So it's not that big of a deal. Okay, so basically, yeah, we advanced the thread card. Once we've gone through everything, we remove the threads that needs to be removed. And then we will do what? We basically start over, so we need to move you down to 0 again. And I guess potentially here we could also check like if we should exit, I guess maybe. There could actually be, we could actually return some kind of event here. Advanced event. Which is like either continue or quit. And here we can say like if we have any items left, we just continue. Otherwise we need to quit because we don't have any threads left, so we have to quit. I'm just going to ignore the pipe threads at this point because the other threads should always wait for the pipe threads through the kind of the code, so I won't really worry about that right now. So anyway, okay, so that's good because you can create this event thing very easily here, and since we call this function and we move the we could also just return from this and then have the caller kind of check the state to see if we need to continue or quit, but it's kind of hard to say that, okay, well, did we need to check okay, is the counter at 0 and this is true, then we continue, otherwise we quit. It's a lot easier to just have, because we have basically the flow already built into the function, so it's nice. We could just return this event, and if we get down here we can see the continue, so the caller would now look at the result of this function and just see, okay, should we continue, then we continue, should we quit, we should quit. Now the only thing missing there is okay, well, how do we get the exit code? But I guess we will figure it out. So so now what we can do is we can get the current thread, which is just going to be super easy getting this here, and then we'll use that. So we'll get the thread is going to be context get current thread. So that's our thread there, and now the thread should have the instruction current instruction, so we could move this to the thread instead. We don't need to have it here. Let's move it to the thread context. Actually, we can move it here as well. Current instruction, and this is gonna be self. Oh shit, we don't have the actual instructions here now. Okay, so we have to do it here. No, not here. The thread context, there we go. That's fine. So self shared instructions, private instruction counter. There we go. Hello, Agent Meko. What's up? What are you making? Is that a Final Fantasy VII reference, by the way? I am making a bash-like scripting language. Right now I'm working on making like virtual threads for it, which is kind of interesting because I've never done that before. So that we can run like the pipelines and everything in the background, in a background fashion. Alright, so we can get the current instruction there. Now let's go back there, and instruction is going to be thread.current instruction now instead. There we go. And this is kind of weird now. We don't, like, if we don't have an instruction, that means the thread should end, right? So I guess if we don't get it, we should like call. We should call like X, like we should like close it. This shouldn't really happen, actually, because the thread should have some kind of exit instruction at the end. So this should not happen, but yeah. Always been interested in coding, but I don't got a PC. All right. I mean, you could look at, you could try to learn through the phone, but it's gonna be difficult, I think. Hello, Metallics. What's up? Welcome back. It's going good. I'm doing some, I mean, to me, interesting stuff with the language here. It's a really nice learning experience. How are you doing? So what should we do? I think we should just also this result. What is this result? Continue exit with the code. Okay. I think what we'll do is we'll say we'll print out the thread ID, and there's no more instructions, and we return null. I think what we do is we actually return, because this function is called here until it doesn't return a result and then exits with success. So actually I don't want it to return null at that point. I want it, because then we quit the whole program. I want it to be continue, I think. Yeah. But then we say we get the result from run instruction here. Now this should probably include the thread as well. So we'll add the thread context here. Okay, and of course we need to adapt this code here a little bit now as well. All right, and you want the thread, and this will be thread private structure count plus equals 1, return result. Also, we want to say advanced thread counter as well, and we're going to switch on the result, and we get either continue, which we return the result, or we get quit, where this means that all threads have quit. So, and we don't have an exit code right now to return, so I'm just going to return no for now, but I'll add a to do here. Figure out how to forward main thread exit code. All right. And we can remove this because that's unreachable now. Okay, I think we're on to the main course here to fix all these now. So this should be like thread private stack append instead. Yeah. Anything else? Structure counter. I see one on there as well. Probably not going to be that many fixes we need to do actually. I think that's it. Oh. Map adder. Where is that actually? Because I'm pretty sure we could probably it depends. No, this shouldn't be in the private. This should be in, yeah, this should be in the program context or the shared context or both. Yeah, I'll just add this over here. And why it doesn't need to be mutable. Whoops. Stack start is over here, so I will move you. Actually, we'll just have it over here. Actually, same with page size. I'll just move you. These things could, like, they could change. Probably they could also be like per thread or something, but whatever. Okay, so if we can have, then we return continue. Wait, yeah. If we have more threads to go through, we return continue, yes. Now, oh yeah, I forgot about something as well. value ignored. Yeah, we don't care about that. I forgot about one thing. If we're currently churning through the threads, but then we're suddenly encountering a thread that was removed, we should skip that thread actually. So when we advance the threads, we shouldn't really care about the removed threads. So we increase the counter, and we'll have a while true here, and we say that let's see, we do +1 if so we get the thread actually if we just get current thread, and if the thread if threads to remove has or contains thread ID, we will continue, otherwise we'll break. So we're gonna continue while the new thread is in the remove bin. So we skip through those. If the thread wasn't in remove bin, we go out here and we break the while loop, and then we check these things. Now it's also important to check if we're at the end. So if we're suddenly over here, we should actually do this part over here actually. So what I'm gonna do is I'm gonna break it. So we'll break there, because the breaking makes us go out here, and this would be false, so it wouldn't go in there, and then it would remove all the threads and do all this stuff. So there we go. If I am correct, that is. And now you're complaining about the stack starts. Let's just do this. And now these are just plainly out there. Same thing over here. All right. Now, do we have map adder? No. So let's add map adder, and we'll simply return self-shared map adder. We'll forward that on, and now we have map adder here. There we go. Okay. You want the data, so this is going to be the read-only data. Instruction counter. Oh. Resolve address. So now you actually need the thread context. That, I mean, that's solvable because we should have it. Yeah, we have it there. So we just add the thread context here. You're writing a very simple interpreter. I've been writing for 2 days. We're already capable of generating AST. I've written an AST printer. Nice. Nice going. It's awesome when you build something and it like when it outputs nice things. It's just a nice feeling. What are you interpreting? Is it code or something else? I'm guessing it could be code, but I mean it could be, you know, a CSV as well or something. Anyway, let's see, thread. So now this should be thread private structure counter. All right. Yes, you are a function. Oh, and you apparently want to be a. Wait. Why do you need to be a pointer, actually? You don't. So there you go. No field name refs. Right. So this needs to be thread local as well. There we go. And we'll have thread private refs. It's gonna be really interesting to see if any of this will work. Thread. Oh, you also need thread now. Thread. Anything else? That's it. Okay, let's just fix the debugger here. So here, basically the same thing. We need to get the thread, get current thread from the context. Wait. Oh. The evaluator context. That's the thread. Yeah. Actually, this is shared. Or is, well, okay, whatever. Cool. Wait, that's it. Okay. Actually, no, it's not it. Because we need to also, after we've stepped through, actually no, that is it, because this takes care of the thing here. Okay. And this doesn't actually look at the thing. Oh, maybe that's why the debugger actually crashes once we're done, because this doesn't actually return anything. So we should actually yeah. So, well, okay. The step function is called from here. Yeah, so we could totally look at, or just return this actually. yeah, let's just return that. So this is now a running event. And we can switch on this to check. If we need to continue, we return continue. If we need to quit, actually, you know what? We need to check or else. If we get an or else, that means we should quit the program successfully, basically. So yeah, we just return quit here because the running event has quit and continue. Okay, and then we switch on event, and we basically just return the same thing. But they are technically different enums, so we can't just return this because this is a different enum. Actually, it doesn't have quit, it has exit actually. Okay, exit. And I mean, okay, what we could do is we could print out process or program exited with code. I think we formatted actually. I think so. We format it. Yeah. And then we return quit. All right. Okay. So, okay. Is this gonna work now, do you think? I think not, because we don't actually spin up any threads when we start. So that's a thing. It's like we're going from having just one main thread to having support for multiple threads, but then we don't actually spin up any threads. And then we just try to run the things, but we shouldn't have any threads. So this should actually, we could test this out, because this should just exit immediately right now. We even get some error here. Yeah, okay, we get out of bounds because we don't have any threads. So, okay, let's look at the context. Could we just add a thread maybe? We could do like init, and then we could have a function that is like add main thread or something. Yeah, sure. No. What am I doing? It's just gonna be this with allocator error void, and then this is just gonna be self threads. Well, it's just gonna be like spawn thread actually, and we don't really care about the ID. So there we go. And then I think we go over here. We initialize the evaluator. And do we spawn a thread here, or does this spawn a thread? Because we're kind of sending in the context here and we have responsibility. We could also just say here we could run, we get the context. Whenever we get the context, we also do add main thread here. Thank you, Piano. Welcome back. Missing struct field shared. Yes, that is correct. You are missing that. So let's add that. And now we should get a complaint over here, but this is simply self-shared as a pointer. There we go. We'll see, Piano. But thank you. You never know what's gonna happen in the land of programming. Okay. Let's go to the debugger and we do the same thing here. Where's the thing? The loop is called from where? From here. Init. Wait, I'm confused. Oh, right, we have the evaluator, right? Yeah, okay. Well, where's the compile? Oh, maybe it's done like from outside. Okay, it's from here, right? Compile, and then the context. Okay, so let's do add main thread here. There we go. Okay, now let's test this. Hey, it works. Everything seems to work. I see one issue. Not sure what's going on here, but yeah. Okay, cool. So we got the we translated our structure into supposedly supporting threads now. Do you think is Parrot OS actually good for beginners? I have no idea about Linux distributions. I actually watched a video about a bunch of them by some person who seemed very knowledgeable about it, and I think what he put in good for new beginners was something like Mint. I don't remember what else he put there. But yeah, that was one anyway. I'm just gonna be away 1 second here. All right. Sorry. The thing is, I haven't actually used like Linux as a desktop environment for like, I don't know how many years. So you shouldn't really. It depends on what you need it for. Like, are you just gonna use it for development, or just gonna use like, are you gonna use it for your actual host OS in a desktop environment, or I think it depends on what you want it to do. So yeah. Like, do you want it to be like a Windows replacement, or yeah? Either way, you should look for other sources, because I'm not that well versed in that. I just use that. This is what I use because it kind of works for me, and I mean I'm using Windows, so you know you shouldn't listen to me about Linux desktop distros, but yeah. You want to be a hacker, okay? Why? But okay. Yeah. Well, I'm, security. Yeah. Okay. Well, I mean, yeah. I mean, there's a lot of resources online for that you could start looking at. I'm not really into that world myself. Like, I just think it's boring to me. It's I don't know. I like to build stuff. I don't really want to think about defending my code against intruders. Even though it's an important subject, of course, and if you want to do anything you want to put out on the market that users gonna use, then of course it's gonna have to be safe. But then you can hire other people to actually do the security if you don't want to do it yourself. But anyway, yeah, that's really cool. I think there's probably a lot of work as well in that sector. Probably. Don't take my word for it, but I haven't really done any research in that area though. But I mean, it feels like it should be. Anyway. But yeah, as I said, like, okay, well, also it depends on what kind of cyber security you're talking about, or security. Like, is it on web-based, or is it like on Linux machines running on servers, the kind of, I don't know, hacking the kernel, or hacking, like, it's so many different areas and levels to it as well. There's a lot of it, yeah. A lot of work in this field, yeah. Yeah, I mean, probably. I haven't really, as I said, I haven't really checked, but since there's a lot of like generic programming jobs, there should be a lot of security jobs as well, because that goes hand in hand. So, okay. what to do now. So we have like the basic structure now for threads. Okay, so so now we're back to the original issue here, which is the pipes. So we kind of have this structure now. We have like, okay, we have the main thread. We don't really have the sleeping mechanism though. That could just be, that could be some kind of, I'm thinking like you could have an instruction that tells the thread to sleep until another thread has exited. And then you just give it the ID of that thread. And that ID would just be stored on the thread. So we could basically just have an optional field on the thread context, which is like waiting for or something. And then if we say, for example, wait actually we need self, then we say that waiting for is equal to ID, and there we go. And then it's gonna do that. And then let's see, we have also when we advance a thread, let's also make a function here, convenience here, for is thread asleep or something, or active. Is thread active? Get a thread ID. And we will check. We'll get these. Actually, get thread context ID. If this doesn't exist, actually, I'm gonna. Actually, if it doesn't exist, it's not active. So I guess we'll return false. All right. So then we get the thread. We will check if it's slated to remove. We will return false as well. And then we also want to check return thread. So we check here if thread has a waiting for. I'm just gonna check if this is not equal to null at this point. We'll do the, maybe, I think we'll do the processing of that later, perhaps. I live in Sweden. Let's see, so we're checking if we are not, if we're, yeah, this would be false, then true. So it's true, it's active if this is not null, yeah. Or I mean, it's not active if that's not null. That's like triple negative. If waiting for is not, no, if waiting for is populated, we are inactive, yeah. Why is it that, Piano? Where do you come from? The grass is always greener on the other side. Okay, so now we can, instead of doing this, we will say okay, this is gonna be let's just do if it's active, we will break. All right. So either we're at the end of the list, we break, or it's when it's active, we break. Otherwise, we continue until we hit either one of those conditions. Okay. Nature mountains, everyone is green. Yeah, I mean, we do have a lot of forests. There's a lot of nature. And like up north, there's even more nature. There's more mountains as well. And down south, it's more flat. So it's like it is a long country, and it's like it's different. It's also a little bit different, like if you're at the south or at the north. But I guess I mean that's true for most countries, I guess. Expected type from thread. Oh yeah, so this is the ID. There we go. But yeah, I mean I like it. I wouldn't move. But that's just me. There are many people who move as well. Because, I mean, the one thing I guess that most people are annoyed about is the cold. And maybe the darkness in the winter. But then it's like a contrast as well, because in the summer it's very bright and warm. So, well, it's not as warm. It's not as warm as in other, like in, if you the further down south you go, the warmer it's gonna be. But no, it's fine. It's fine. Don't worry about it. Okay, so we've got this thread counter. Yeah. So now we have this convenient function instead, like checking if the thread is active. So that's good because we need it in another place now as well. But I did forget where we. Oh yeah, it's the sleeping thing. Waiting for. That's right. So what do we need more for this? We need to also process this to check, like, are we still waiting for something that had quit? Then we can actually set that to be null, to not null. Maybe we should process it here actually. If okay, let's do this. If we're waiting for something, let's do this instead. Let's do like process waiting for thread and then we can check afterwards. So we'll have the process waiting for. Yeah. It's complex for me anyways. I've never done this thing before. I mean, I know about threads to a certain extent. Like, I'm not a thread expert or anything like that. But you know, I'm understanding the concept and why we want to have it. It's not like I'm just adding it just because I've heard of it or anything. I'm seeing a logical path to needing threads, and then I'm thinking like, okay, well, how can we implement them for what we need for this? But it's really interesting, because I've done like a evaluator and everything before, but not with threads like this. So process waiting for. So we'll take a thread and we will actually, this needs to be mutable now. Wait. No, I think we'll move this into private actually. Yeah. We'll move this in here. Yeah. Because I want all of the mutable stuff in this pointer so that we don't get out of sync with this. Yeah. Because the thread context is like copied everywhere. So yeah, there we go. So now we don't need to send this mutable here. It becomes clear when you look a little longer. Yeah. It's not looking complex. Okay. So you thought it would look complex first, and then when you looked at it a little bit longer, it wasn't complex. Yeah, I mean that's that's kind of tricky, because the mind can actually trick you then because it's like, okay, well, let's say you're learning to drive a car, right? In this beginning, you need to learn all these different things, like especially if you're like in my country, we have a lot of manual cars, like manual transmission, so you have to do that and it's a lot easier to learn like to drive an automatic, but that's not the point. But anyway, there's so many things you need to learn, and you need to kind of understand intuitively, basically, while you're driving. And in the beginning, everything is hard, and like you're gonna get stuck on a lot of things, and you're gonna drive like an asshole, and then you learn the things, and then it becomes easy. And then but then you're kind of blind to the fact that it was actually hard at the start. So when you see like a noob, you get angry instead of, or well, many people anyway get like angry when other people like make mistakes, or yeah, just don't realize that, hey, it's actually complex. It's actually not easy. It's a matter of perspective, right? It's a matter of like how much experience you have and all that. So yeah, but that's the thing, like the word complex, I feel like is actually playing into that. Like it's something that looks complex to one person might not be complex to another person, but then it's also like, okay, well, a real test would be to actually leave the code for a while and then come back and then see if you can easily pick it up again. If you can, then I would say it's a good written code. But if you get back and you are like, what the hell is this? What did I think when I wrote this code and all that? Then it's like, okay, well, maybe it was like, you may have thought that it was simple code, but it was actually maybe not simple code. And then you learn over time, like you can kind of see the signs. And but it's also like you can see the signs that, okay, maybe I should fix this right now because it's gonna get ugly later. But then it's also like, okay, well, how much energy do I have to spend on this now? Like, do I really want to perfect this piece of code right now? That's also part of it. So it's like, not every part of the code needs to be perfect and optimal, you know. That's actually like a huge waste of time, a lot of times as well. So it's yeah, readability and all that is like, it's not an easy topic. And then it becomes different when you're working together with other people as well, because then, you know, other people's gonna read your code, so it has to be more approachable, more readable at that point as well. Private. There we go. Yeah. All right. Process waiting for. So we're gonna check now. We're gonna check. So if you have waiting for, and we're gonna take the mutable version because we want to change it if it actually needs to be changed. So oops. All right, good. Well, how long have you been coding? Let's see. Okay, so now as we just check if the thing that we're waiting for is, so waiting for is an ID. It's kind of, yeah, it says usize here, but then I actually assigned it as a thread ID. I wish it would say thread ID instead, but sometimes you want to see the end result of the type, sometimes not. So it's hard for the compiler to know, or the LSP to know, or whatever. Yes, you, Piano. You start 14. What do you mean? Waiting for, yes, that's the thread ID. So we have the threads. So we need to check if the thread exists or if it's slated to remove. I think we'll check this first because it's easier. So if this contains waiting for, should be the key. If this contains, we are gonna say now waiting for should actually be nullified and then we return, because the thread that we're waiting for is being removed. Okay, and then we're simply gonna loop through our threads and check if the ID is equal to waiting for. If it is, we can simply return, because then we are still waiting. But if we went through the entire thing without finding anything, we have to now set you to null. So now we're not waiting anymore. Okay. And let's join this here a little bit. I need a thing there for that. Expected use size. Wait, what? Oh. I see. So we have to do this instead. Okay. There we go. So that's basic, like a thread can wait for another thread. We're processing it while we're trying to check if it's active or not. And so we're checking, okay, are you waiting for something? Then is that something removed? Okay, then we clear this flag and we return, or the ID there. Otherwise, we're looping through all the threads to check if it's in the list. If it's not, then we return. And this is probably not needed, maybe? I'm not sure. There could be an edge case where this is actually needed, so I'm gonna keep this in here. But otherwise, we didn't find the ID in the threads list, so we have to clear this and then we're done. And then after that, we're simply checking, like, okay, are you waiting for something or not? So if you are waiting for something, we are not active. There we go. I need to do some mental gymnastics to actually... This Boolean logic sometimes messes with my brain. No, it's just you talking right now, Piano. Two and a half years, alright. I was 15, so wanted to learn coding, started downloading apps like PyDroid, 3 terminals to my phone. Okay. Trying to create applications, games using the Kiwi library Python. Okay. I was trying to create text-based games in Python. Cool. So I started to expand to new areas. Now I realize that's not enough. Not enough? What do you mean not enough? Not enough for what? I've been programming for 30 years and it's never enough. There's always more stuff out there to learn. And it also kind of, well, there's always going to be more stuff. Like if you don't, if for some reason you have learned everything there is to know right now about programming, there's always new stuff being invented all the time. So there's never going to be an end of things to learn. Even if you're like super efficient, you learn everything, you can still invent new things. You want to do new things that have never been done before. That's cool. I mean, you could go into like, I don't know, programming language research. That's pretty cool. There are like, you know, in the academic world, you can do a bunch of stuff there. Because that's, you know, research is where new things happen. Of course, new things happen in other places as well. I mean, companies have research departments as well. But I think if you want to go into research, you have to build up a foundation of knowledge as well. So you first have to become like a competent programmer, I think, in order to start doing research. But I don't know. Hey, I've never been in that field. That's just my hunch. I would assume that anyway. But yeah, I get your feeling there. Like it's fun to think about, hey, I want to do something new, something that no one has ever thought before. Like I want to explore, and that's why I looked at a bunch of different like programming languages. Like, have you explored like what kind of programming languages there are, and you know what kind of because there's a lot of things out there, and there's like even, you know, these old program languages that that has kind of been forgotten, that might have things that feel new, but they're actually super old. So that's the thing. Like if you want to be like a researcher or anything like that, you have to kind of, I think you have to kind of build up knowledge a lot. How would you know if it's new if you don't know a lot about programming? You have to build the knowledge. I'm not saying, by the way, I'm not saying that you don't know a lot about programming. That's not what I'm saying. I'm just saying, and for a hypothetical person that needs to become knowledgeable. Yeah. Oh, but what kind of thing are you thinking about? Like, do you have an idea of what you want to explore? What areas, like in coding, you want to explore? Let's see, where are we now? So, right, that was the waiting for. Okay, so we basically have the sleeping thing now. I'm gonna go to debugger. There was a thing I saw with the printing. Where was that? I think it was like run command. Wait. Run command. We consume that. We parse the command. We handle the command. If it's step, we run step. Now, the thing is, when we consume and we parse and we handle the command, where is the part? Okay, I think what's gonna happen is that when we step, is that we need to print a new line here. Yeah, there we go. Because it was like printing this up here before. Okay. Cool. Yeah, that's something to think about. What was the last project you made or worked on? Okay, what do we want to do here? So we basically kind of have this yeah, we do have this now, because it's gonna skip the main thread if we're if we're sleeping, right? So that's implemented here, and then this is not really implemented, but we can exit the thread, sort of. We don't actually, yeah, we don't have, what we don't have actually is when we have an exit statement. Result. So this is like the main thing. I think actually what we want to do here is we want to check, before we do this, we want to check what the result is. Is the result going to be if we have a result and we switch on it? If we don't have a result, we actually need to kill this thread here. So this would be like close thread ID, because then when the result is null, that means the thread exited, I think. Or does it actually? Wait, where do we actually return null here? We don't. Okay, so it's not optional. I'm doing message app right now. Okay, cool. I want to make something that has components, something that can have features like a motherboard, for example. So, do you mean like an emulator? Like a virtual machine or something like that? That you can like run programs on, or I mean there's no shame in just building something to get experience, like, and then you can, like, in the meantime you can think about, okay, it would be cool to do this or that. I do it all the time, like I'm constantly coming up with new ideas, even though I should like try to finish the ones I have. Yeah, I want to make robots or machines. So actually like an actual physical motherboard. Physical robots. Okay. So more like embedded programming. But you want to code every part of these. Okay. I don't know too much about embedded programming, to be honest, but it's a cool area. exit code. Actually, you know what? Let's just do this actually. Let's just have thread exit codes. Okay. And then when we close the thread, we actually also bring the exit code that we can then thread exit codes. We can put the thing, oops, there. Yeah. To earn money to support myself, but since it will take a long time to get the education I want in this field, I may not have enough money to live on. That's the sad part about being a student, is like you barely have any money. Yeah. Okay, and then we put that there. So we could have continue as well. I know we don't really do anything there. And then we do this. We advance the thread counter. So now we actually do have the thread, the main code. So what we could do is we could return context. We could just get main thread exit code here. Which gives us an exit code. And we simply return thread exit codes get 0, which is the main thread. Should be the main thread anyway. And we unwrap that because we just assume that we have it. No, nothing is impossible. I mean, I think an education is a good start because that area is like, it's like, how else would you start to, I mean, get the stuff you need to try those things out? And you're also gonna learn, you know, you're gonna get a lot of information about how it's actually done, of course, as well. What the hell is this? Oh yeah, so return exit. And here we return content. What the hell is this? Oh yeah, this is void, so just you could just do this for void. All right. So also now the main thread is supposed to be able to close now as well then. I wonder how it closed before though. Maybe it was just like doing this. There were no more instructions. But then we should just continue, so that's weird. How did it exit before? But I mean, we should have gotten an exit here and continue to return the result. Right, okay, maybe that's how it was, why that happened. But now it's like if we run out of instructions, we should actually close the thread with success. So I'm gonna do try self context close thread ID with success, and then we continue. Actually, we should advance. Yeah, we should advance the counter. Should this be deferred? Then no, yes. No, we can't. We can't defer it. I'm not sure what to call this here. Hello, Thomas. What's up? Welcome back. Yo, doggin. Ooh. Yo, 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 yo. Yeah, we want this to execute. So basically, yeah, I'm just gonna say advance the counter, which gives us a result, I think. And we just do this. Self. No. Evaluator. Oops. There we go. Let's actually do this. And instead of just continue, we do that. Okay. Okay. That works. Everything works. Step. Oops. Go through, step through everything. It's interesting, like in debuggers, it's like, yeah, each statement has, you know, a bunch of instructions. I guess it's like defined, like what I'm trying to say is like, okay, well, each statement is like, okay, well, we might stop here, and then when you execute a statement, you actually execute a bunch of instructions that correspond to the whole statement. It's interesting how you choose, like, what should be considered a whole step through and or not. All right, go to sleep. Good luck. Okay, but now, yeah, we have that. So let's go through this again. We have the sleep, we have wake up, we have execute the next and stuff. We actually do have the exit code now that we can get, so that's good. Yeah, same thing here. This all should work. The pipe threads we don't really have because we don't have the concept of pipes yet in the IR. Which is the whole point of this virtual threads. But I mean, yeah, now we have support for the pipe thread, so we could actually we could start thinking about how the pipes should work now. And what we need to support here is we need to have generic sources, which is going to be either like an executable or a file, you know, a file. Basically it's a file handle. Slash destinations, I guess, because they are kind of the same thing, except you read from one and write to the other. So we have the executable, which is a file handle. We have potentially then you know, you could call a function which would produce kind of like an execution context. Like the thing about functions or blocks, we should talk about blocks first, is that the blocks as pipelines, if you look at this block here is actually a lot more complex than it looks like. Because if we want to potentially be able to pipe this into cat, let's say, what is going to happen here? So what we need to support here is basically suspending the block execution. The block should be actually spawned in its own thread, actually. That's what I'm seeing here. Each block should be spawned in its own thread. I guess if it needs to. Maybe sometimes you don't actually need to do that, but let's just say we do by default. Because then you could suspend the thread here until, and then the what we emit here actually, yeah, the whole block should have, it's kind of like a process. It has its own thread. It could potentially read from standard in, but it also puts out things to standard out. And then that, whatever it, so yeah, so that's actually better than I was thinking before, I think, because I was thinking like, hey, we should, like, when we get to this point, we're gonna emit this as some kind of pipeline part that we kind of hook into here. And then when it's consumed, we can continue execution, and here we get another pipeline that we can connect here. I mean, that's, in theory, that's what's happening, maybe you could argue, but what I think we should do is, like, we should spawn this as a separate thread, a virtual thread, and it's gonna have its own standard out and standard in and all that you can then, that you are then connecting with this pipe. Whenever we continue execution of this, it's outputting this into its own context. So maybe the threads should actually only ever have the threads themselves should have like standard out, standard in as well. Yes. That seems like a good thing. So when a thread executes this, anything that outputs to its standard out, maybe we don't even need, no, we do need context, because we need bindings to bind to, like, all this is going to be put in this binding here, but maybe it's as easy as just putting this in its own thread as well, like this whole, like everything that is in the binding here is put in its own thread. I mean, it doesn't really need to be a thread, to be honest. Well, actually, there could be other things going on there, and then we just wait, like, since it's a binding, we just wait for the thread to complete. Yeah. And then I mean, yeah, and then what you read here is basically this block here. It's echoing these things, but since it's piped, it won't actually echo those things straight away. It's gonna, this whole thing is gonna build like a pipeline, and then the block will be part of the pipeline, and so this will be spawned. I don't think any block is gonna be spawned as a thread anyway. I think, like, if there's a difference, there's a couple of different scenarios. Like if you just have a naked block like this, let's say. Now this doesn't technically need to be its own thread, because it doesn't bind to anything and it doesn't pipe to anything. It's its own kind of thing. So really, it doesn't really need to be its own thread. However, in this context, it needs to be its own thread, because when it's piped, we need to be able to talk about this expression and its whole output as a thing, which makes sense to do in a thread, because the thread could execute through the block code and wait for things to happen here. Like even for something as simple as just an echo hello, we need to talk about how that should work. Hola Discordianism. What's up? We're doing end of the year chores, rewriting a bunch of scripts in Zig. It's been fun. Oh, okay, cool. But were you one of the ones that was trying Zig for the first time now? Or? What is happening when we do this? We should wait for it to complete. We could make a virtual thread that we wait for, like just by principle. And then the inner thread would just spawn this. But the thing is, like, we need a special case for spawned processes. Like when you call wait on a thread, Maybe it's like at the end of a thread, it actually calls wait on all of its processes or something like that. We should really only have one process though. We could do that. We could always map each process to one thread, and at the end of the thread it just calls wait on its processes. We could bookkeep all the processes spawned. Yeah, that seems like a very easy solution. Okay, let's do this. Private context. Let's have like, we should really only have one process. Potentially, it's not even certain that we have one. So we'll just have one child process here. No, but I played with it sporadically over the years. Finally coming together for production use though, so I'm committing more time to Zig. I see, cool. What was the project, if you don't mind sharing? You might have told me before, but sorry, I don't remember. There's been many people talking about their projects and so we'll keep one process in here because we shouldn't have more than that. 1 or 0. And then for the thread, wait is waiting for another thread. Wait for. If we call wait, that means we want to wait for this thread to exit. Which means we want to wait for this process to exit if it's there. So we're gonna say if we have a process, we're gonna wait for that process. Also, this should return an exit code, and we're gonna say it also could be a wait error. So wait error, wait child, wait error, and we'll do try, and then we'll do from term. There we go, and we will return that. Otherwise, I'll just return success. Okay. And then I think also for safety, we're gonna say actually what we could do is we could defer self private process. It's null. All right. So that would actually block until the process is done with its thing. And now, what do we need? What we need to do is we need to go to the evaluator and we need to go to call, and instead of doing this, we're going to do wait for spawn, which will do some stuff. This is like a weird quirk here, but it will basically do some things, and then we have to wait. So this will basically make sure that we actually run the thing, and we can call, you can call spawn and then wait for spawn, which will actually spawn the thing and actually run the child process, but then when you call wait, it will wait until it's done. So this will become the blocking, but now after this point we've actually spawned the process and it's churning through. So instead of calling wait here, what we'll do is we'll say well, actually we could do like context spawn thread. So we'll get the thread ID here, and let's get that thread there. We could just return, I guess we could just return the whole thread context, but whatever. We get it. We should just unwrap it at this point here. Okay, so we have the thing, and then we should set the process to be child. Okay, and we don't wait here, but what we do no, that's what we do. I'm pretty sure. We set the process there to child. So now we have a new thread, right? However, should this happen in the code actually? Because the main thread needs to wait for this, possibly. How do we hook that up? I mean, maybe what we could do is like store the process, the new thread ID in a result, in a ref or something, and then we can use that, like the main thread would but after the call it would get the ID and wait for it basically, and it would like it depends on the context what you want to do. Not all calls are the same, so it depends on what we do with the call. So I think the call should just return the thread ID actually. I mean, and for now we could just say that the current thread, which is this one actually, so we cannot call this thread. Let's do like child thread. And this is the child, whoops, thread ID. Okay, we could say thread and then wait for child thread ID. So we could do this to kind of make the parent sleep for the child to complete, but then it's like it depends on the context. Like if you just want to, if you want to pipe this call, that's a totally different thing. So this goes back to now to how to implement the pipelines in the IR, which is going to be a really interesting thing, because I think we need to build up a bunch of primitives now, a bunch of instructions, so that we can enable the pipe creation, the pipeline creation here. So that's going to be something to think about. I'm pretty sure I'm not going to be able to do that now, so because I need to leave here now. It's becoming a bit late, and yeah, this is a really interesting problem here. Why are you don't need to be mutable, and you are private. Also, this doesn't need to be mutable. And now what we need to do is we need to go to the evaluator. So this would make it work for now, I think. We could test it. We need to go to the evaluator, and we need to go to, where is it? Here. And we need to see, okay, when we advance the thread counter, we also want to look at the current thread and call wait. No, wait. No. This is where it, when we close. Oh, so we already kind of do it. When we close the thread, we actually want to call wait on it, I think. Perhaps. Maybe not always. Maybe that should be determined in the instructions instead. But we could just we could do we could get the thread, get thread context ID, and we will call wait on that. And we get an exit code. Oh, I see. Let's just do null then. So either we have it or we don't. So let's do like exit code equals, if we pass an exit code, we should use that, or else no, actually let's do this, wait exit code. And then the actual exit code is going to be like exit code or else wait exit code. So many exit codes is like we could pass it in here, we could have one already, maybe we have, no, maybe not, but we can wait for that. That will wait for the process potentially and give us that with exit code. The thing is, that's not always the case either. Like if we want to have that, well, I guess since we can override here, that's fine. All right. So now whenever we close the thread, we also wait for it to end. You all right, let's do that then. Okay. There we go. Let's see if this just works now, and then I will call it here. Oops, not you. Let's just do run. No. Why did we get so many hellos? We got like a lot of them. Is the instruction counter not incremented? Oh, wait. No, because here we should just wait and be done. Oh, you know what? Okay. I know what's going on. We're basically forking. We're basically fork bombing ourselves. Because when we spawn the thread, it's what is it spawning in? It's spawning at instructions 0 at the start. So that's we're forking. But we're forking like at the beginning of the program. So this child thread is like spawning at the beginning of the program. That's also another thing. But it should also be. It should be sustained as well. It should be put to sleep basically. Or we could do this. We could do a trick here. We could say child thread private instruction counter is equal to shared instructions length. So that will cause it to end immediately, basically. No, not this one. Index out of bounds. Context 183. Evaluator 51. Right, because we're trying to get it here. But what the hell, why? Huh? No, shouldn't this be equal? Okay, there we go. Cool. All right. Okay. So we actually spawn a thread now. We spawn a thread per like per thing that comes out here. We spawn not an actual thread, it's a virtual thread. Okay, we're spawning a virtual thread for each call here, and then we instruct the main thread to wait for this for the new thread. And then we also wire up the process that's been spawned to that thread, so that that thread then will know that when we wait for the thread to close, we actually wait for this process to finish before we continue as well. Which means right now that every time we encounter this, we will block, even if it's part of like a pipeline, let's say. So we don't have streaming yet, but we're gonna build the building blocks to be able to get this working here. But yeah, that's gonna be it for this time. Thank you very much for joining me here and talking with me today, and I hope you have a nice day, and I'll see you later. Bye bye.